Welcome everyone to the beginning of Organic Chemistry 1. We're going to go ahead and start with an introduction in Chapter 1. This will be kind of a review of some of the topics that you should remember from your general chemistry. These topics are going to carry on. We're going to build on them in organic chemistry, so it's important to kind of know these topics very well. So if you believe that you need to go back and review these topics, please use the resources that I have given and make sure that you have a good foundation in these areas. So some of the things we're going to start with reviewing again is just basics of the atom, orbitals, what's an ionic bond, what's a covalent bond, reminders of Lewis dot structures, the octet rule, polarity, electronegativity, and then talking about formal charge. Okay, so into section 1.1. Just a reminder of the makeup of an atom. Remember, an atom is mainly composed of three particles. First, the neutron, which has a neutral mass, or excuse me, a neutral charge, and a proton, which has a positive charge. These two things make up the bulk of the mass of the atom. In fact, they're situated in the nucleus. And then there is the electron, which has a negative charge. The electron is much smaller in mass in comparison, but still ultimately very important. The electron is the cause for most of the chemistry or the interaction that we see in general all over. One other thing to note is that the proton is the distinguishing factor of an element. So the number of protons in the nucleus of an atom is what we call the atomic number. If you look at the periodic table, anything on there has an atomic number. It's labeled number. And that distinguishes it as an element. It makes carbon carbon, it makes oxygen oxygen. And this is distinguished by the number of protons that are present. So electrons, again, are the cause of most of this chemistry, and they are very interesting. They are called a particle, but ultimately they act more like a wave. It's because they're so small. They interact almost like light does. So they behave more as waves than particles, and we define this through the Schrodinger equation. And this wave-like behavior is actually captured by our description of it via a wave function, or what we call an orbital. Every electron has an associated orbital, and the electron occupies that orbital. The shape of the orbital is a reflection of the probability density of the electron over space. What that means is just the shape that we give it. For example, down here, this circular shape, this is the area of probability that that electron will exist in. So this is the area that is most likely to exist in, with some areas being more likely, more dense, and other areas being less dense. The energy of an orbital is a reflection of the stability of the electron in it. What that means is the electrons, some electrons are more stable. Usually these are electrons that are closer to the nucleus in tighter, smaller orbitals. That means that they are usually more stable. Whereas some electrons, as they get further out in these bigger and bigger orbitals, these orbitals further and further out, are less stable, less likely to stay within that area. That's why you see in these very, very big atoms, like in uranium, they're unstable and they're usually giving off particles. So we can characterize these orbitals, and we give them associated numbers to characterize them. These are called quantum numbers, and they help us characterize the energy level and the shape of the orbital. The first of these is called the principal quantum number. So if we're talking about elements, we're talking about their quantum numbers. One way to easily show the principal quantum number is using the periodic table. This number, n, is related to the energy of the orbital itself. Remember I said orbitals that are smaller, denser, closer are going to be more stable, whereas other ones are going to be less stable. So as we go down the rows of the periodic table, you actually increase in your quantum number. So all elements in row 1 have a quantum number of 1. Elements in row 2, quantum number of 2, etc., 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 as you go down. This is an easy way to showcase the quantum number. The next way we characterize the orbitals is based on the orbital quantum number, and this is related to the shape of the orbital. So as we go up in the principal quantum number, we also start making different shapes, different density areas. The ones that you commonly will see are, firstly, the S-shaped orbitals, which are spherical S. The next is the P-shaped orbitals, which kind of have this, we call it a dumbbell-like shape. Although I haven't seen very many dumbbells that look like this, but you get the idea. And then lastly is the D orbital. They have a variety of shapes, but usually they are classified as this kind of flowery X shape. So again, that was the orbital quantum number, and that relates to the shape. The next is the magnetic quantum number, M, which is related to the shape as well, but it's mostly related to the directionality of the orbital. So I'm going to bring you back to this picture. You can see one of the easy ways to look at this is in our p orbitals right here. So these are all p orbitals. You can see that there's 3 p orbitals. That's because they actually have 3 of these magnetic quantum numbers, meaning they exist along 3 different directions. There's one that goes along the x-axis, one that we can characterize as going along the y-axis, and the last which goes along the z-axis. So based on this, you could guess how many of our M numbers do we have for D orbitals. So you can see the directionality of the D orbitals here is shown as having 1, 2, 3, 4, 5 different options. 5 different directions. Okay, and lastly, one of the last pieces of information to characterize our orbitals is the spin number, S. This is actually related more specifically to the electron in the orbital. Remember, the orbitals are a density map of an electron. So we're talking about an electron in general. It's just that the electron takes up space. But the electron can also have spin. So this is a magnetic property of the electron. The electron can either have a 1/2 plus spin or 1/2 minus spin, shown here basically as 2 different spin directions. You can see one is counterclockwise versus clockwise. So there was only ever 2 different spin types that can exist for an electron, and that's within any of these orbitals that we talked about.